Today's webinar will be about plastics for 3D printing and how thermal analysis can help in this topic. So first of all, my name is Erika Hahn. I studied physics in Erlangen, and here at Linzheis, I'm responsible for the thermal conductivity measurements and also for thermal electrics measurements. Who do not know our company, just a short introduction. Linzheis Messgeräte was founded in 1956 by Dr. Maximilian Linzheis, which you can see here in this picture. And we're based here in Selb. We manufacture instruments for thermal analysis and thermal conductivity and also thermoelectrics. Here in Germany, we have an own sales and service locations also in USA, China, and India, and more than 65 distributors worldwide. Today, the son of Maximilian Linzheis, Klaus Linzheis, which you see here, is the owner of the company, and his two sons, Florian Linzheis and Vincent Linzheis, are also here in the company and also leading Linzheis. So our product range, as already mentioned, ranges in thermal analysis. So we have calorimeters, thermogravimeters, SDAs, dilatometers. We also have thermomechanical analysis instruments, and a rather big field also is the thermal conductivity, thermal diffusivity range, and we have instruments also for thermoelectric materials, as well for some special applications like thin film analyzing and Hall effect measurements. What makes us unique is that we build customized instruments, so we optimize all of our instruments to the application requirements of the customer and offer also some high pressure instruments, for example, and customize the instruments. Today's agenda will be a first introduction into 3D printing or additive manufacturing, as it is also called. Then I will show you some methods of 3D printing. Then I will present some of the plastics which are used there. And in the end, I will come to thermal analysis and 3D printing, how the thermal analysis can help here, or why the thermal analysis is of interest. So first of all, 3D printing or additive manufacturing. This is another name for it. Describes the manufacturing processes in which a three-dimensional object is manufactured by applying a material layer by layer. The build-up, it is computer controlled, and typically the sample or the material is liquid or solid, and the printer builds then this material according to the model which was created in the computer program. It is also possible to use a 3D scanner for the model, so one can scan an object, and based on that, the next object will then be printed. So traditionally, the 3D printing is focused more on polymers, but nowadays also metals and ceramics or composites of some of these materials can be printed. With the additive manufacturing, one has the possibility to build some small models or prototypes. One can also build some unique parts or smaller parts with parts with a smaller quantity. And the biggest advantage is that complex geometries can easily be achieved. So typically one needs to create first a mold, then do some processes, then weld the parts or mount the parts together, and so on. So there are several processes to have a model which is really complex, and with the 3D printing, everything can be done in, so to say, just one run. The main application field of the additive manufacturing is in general the industry and research. Here, as already mentioned, the models or prototypes are really of interest, and one can also build some tools. Further application fields are, for example, construction and the medical industry, for example, for prosthetics or implants. Another field is also art. So you can build really complex structures rather easily. And nowadays, the 3D printers are not that expensive, so one can use it also in daily life. So an example here are these bricks. So for toys, if you need a special brick, for example, you can rather easily print one, or one can use the printer also for doorknobs, or if some small part is broken, you can replace it rather easily. There are several methods to create this three-dimensional object, but according to an ASTM norm, there are 7 categories in which all of these methods can be summarized. These are material extrusion, powder bed fusion, photopolymerization, material jetting, binder jetting, directed energy deposition, and sheet lamination. In the following, I will shortly explain which material or method class describes what. So material extrusion and powder bed fusion are the most used methods for additive manufacturing. So in material extrusion, for example, fused deposition modeling or fused filament fabrication, there are some filaments which are fed into a nozzle, and this printing head extrudes then the material onto a tray, which is in some cases heated. And here one uses mostly plastics or metals to print. And as the filament or the stream of material is on this heated tray, it cools down and solidifies again. So by that one creates the object and then the next layer. And the layer by layers are put onto this tray. The powder fusion techniques are, for example, the selective laser sintering or the electron beam melting. Here, one can print polymers or metals, and the material is in powder form, and high energy source like a laser or an electron beam melts then the material to achieve the object. And here a big advantage is that the powder which is around the material serve also as an sorry, I got lost. Yeah, so the powder around the printed material is stabilizing the printed geometry, so by that really complex geometries can be achieved. So the powder also supports the object. Photopolymerization, or also known mostly as stereolithography, shortly SLA, describes processes where a liquid material, so a photopolymer, is cured using UV light. The photopolymer here is sprayed onto a build tray, and each layer is then cured with the light. And an advantage here is that since the polymer is cured directly, it is not needed to post-cure the material, or further process steps are typically not needed. So this makes the process a bit faster. In material jetting, droplets of build material are selectively deposited. In binder jetting, it is a similar process, but here not the material is jetted, but the binder, so one has the material in powder form, and the binder is then put onto this powder, and by that it solidifies. Another method is the directed energy deposition. Here the material is melted and bonded by using an electron beam or a laser. So it's rather similar to the powder bed fusion. An image for the powder bed fusion you can see here. So you see here some parts of the already melted material showing out of this powder. And the last class, which belongs to the 7 processes for additive manufacturing, is the sheet lamination. Here, sheets of material are bonded using, for example, the ultrasonic welding or an adhesive. So, as mentioned before, the typical materials for the 3D printing are polymers, metals, and ceramics. And in this webinar, we will focus on the plastics. So the most 2 common polymers or plastics which were used for additive manufacturing are PLA and ABS. PLA is made out of fermentable plant starch, or for example, corn or sugarcane, and thus it is bioplastic and is biodegradable. PLA is really or rather easy to print. Only low temperatures are needed, so the printing temperature is ranging from 180 to 230 centigrade Celsius. The real or the used printing temperature depends also on the manufacturer of the filaments. The PLA has also fast cooling and solidification times, so the printing process is also rather fast. The PLA offers also the possibility to add metal particles, wood fibers, carbon, or similar to the filament. Another advantage of PLA is that it shows almost no deformation during cooling, which can be also enhanced by using a heated tray. The recommended temperature is 20 to 60 centigrade Celsius. The drawback of PLA is that the printed object is not heat resistant, so the maximum use temperature which one can use on the object is up to 60 centigrade Celsius. ABS is also a very common used filament material. The advantages are that it's robust, really light, cheap, and available also in many colors. It also offers the possibility of adding metal particles, wood fibers, carbon, or some other materials to the filament, so that one has in the end an combined material. So by that one combines then also the mechanical properties of them. The printing temperature here is a bit higher, so from 210 to 250 centigrade Celsius. And due to that higher temperatures, a heated tray is really necessary, not only recommended, but really necessary. And here the temperature should be between 80 to 100 centigrade Celsius. And what is also a benefit of the material is that one can treat the printed material then with acetone. By that, one achieves then a smooth and shiny surface. For example, with the bricks, which you could see in a picture, some slides before, is also made out of ABS, and with the acetone treatment, one gets also a shiny surface. The ABS printed materials are, for example, also used in interior of cars, the toys, helmets, housing for electronics, or similar. Since the ABS has really great mechanical properties and is also rather easy to process and print in general. The disadvantages of the ABS are that there are some temperature issues, so it is really sensitive to the printing temperature and the temperature of the heated tray, so that the temperature management is really crucial. And furthermore, the cooling process is rather slow. So by that one has the danger of cracks or some split in the layers, or one can have some curls and warping. Furthermore, ABS creates some dangerous or harmful vapors during printing, so that for the daily use, one needs to take care of how to print, so a further test may be necessary. And of ABS, there are also some combinations. For example, there's also some polycarbonate ABS, and by that, one can also combine the properties of different polymers. The next two large groups of used filaments are PET or PET mixed with glycol. So by that, one can achieve then some different properties. So for PET, for example, the printing temperature is above 260 centigrade Celsius. Thus, a heated tray is also needed. And the advantage here, it is food safe, one can recycle it, it's robust and flexible. So PET, you all know from the water bottles, for example. And PET is also a good alternative for ABS, since here during printing, no harmful vapors are generated. And the disadvantage or the problem here with the PET is that the surface gets scratched really easily. So depending on the application, one needs then to choose maybe ABS if the surface needs to be protected, for example. The PET mixed with glycol has rather similar printing temperatures and also the same tray temperature. The advantage here is that it's weatherproof additionally, so it can be also used, for example, for tools for the garden. It is also food safe, flexible, and has a good strength. But the problem with the PETG is that it's really sticky during printing. It's really hygroscopic and pulls strings rather easily. And as the PET, the surface gets scratched rather easily. And a further problem is that the PETG is rather UV sensitive, so it's not good for applications where, for example, the sun is shining on a lot. Here are the next used plastics for additive manufacturing. So PMMA is also rather used often, as well as nylon. Here, printing temperatures of PMMA are lower than, for example, of nylon. And here again, a heated tray is necessary. Why it is necessary, I will explain a bit later. In this table, you also see always the glass transition range and the melting point of the material, which is also important for the printing process. I will describe it a bit later. Here you see, for example, the PMMA, the glass transition, is at much higher temperatures than that of the nylon. PMMA is often used as a replacement for glass since it's transparent, has a good strength, is shatterproof. But the problem with the PMMA is that it's not that easy to print because it can get opaque really easily depending on the temperature. So here the temperature management is also very crucial. And warping is also a problem with PMMA. What this is, I will also show you a few slides later. Nylon, for example, is also robust, flexible, really durable, and has a very good adhesion between the layers. The problem here is that it has a really rough surface after the printing, but this can be polished afterwards. So here a further processing step is needed. Additionally, the material shrinks very much or more than the other materials during the cooling process. So this needs to be considered as well when printing an object. The polypropylene, for example, is also used. It has also similar printing temperatures than the other materials, as well as the polycarbonate. And here they have also some unique properties. For example, polypropylene has very good mechanical and chemical properties. So it's also resistant against some chemicals. The disadvantage here is also that it's rather complicated to print, because here the adhesion between the layers is not that good and the layers tend to curl. And the polypropylene is not really heat resistant. That is also a disadvantage. And for that, then the polycarbonate, for example, can be used. It's a very hard plastic, has a high strength, and it's extremely durable. And it's good resistant against heat. So one can use the material up to 110 centigrade. So then the printed material. The printing temperatures are around 300 centigrade Celsius, so rather high. And the material shows also a rather high shrinkage during cooling. The polycarbonate, for example, is also used in for bulletproof glass or for screens. And here are also some further materials which are not that used that much. So thermoplastic elastomers like TPU, TPE, TPC are printed in a temperature range from 210 to 230. The heated tray is also recommended between 30 and 60 centigrade Celsius. The advantages of the materials are that they're really flexible, chemically and heat resistant, but they're also rather complex to print and are sticky during the printing. There are also some resins which can be printed or used in additive manufacturing. So resins are more or less all fabricated using the stereolithography, and the resins have a good mechanical properties, and the printing is also really fast. The problem here is that the post-processing is really complicated and not that easy. And also there are some high performance plastics which are used in additive manufacturing, but here the printing temperature is really high, so above 350 centigrade Celsius, and the heated tray must also be at a high temperature. But the big advantage of this high performance plastics are that the mechanical properties are really similar to metal, and they are really heat resistant and show a lower weight compared to metals. And the disadvantage, as already mentioned, is the high printing temperature and the heated tray. And furthermore, a closed chamber is also needed, because here then the temperature is more stable. So now you know some materials which are used with the properties of them, and also which methods are available for additive manufacturing. And now the question is, why is thermal analysis necessary or good when using 3D printing as well? So some of the advantages I already mentioned, like the warping. Warping means here that on the bottom, the edges bend to the top. This is due to some temperature issues, and here the lower part of the material cooled a bit faster than the upper part. It was here really hot. So here then there are some forces which then bend the edges to the top. Further problem can be overheating. So if the temperature management is also not good, if the filament is heated too much, it can cause some touch effects, or further temperature issues can lead to curling, so that here the edges on the top bend a bit. So this is also due to some temperature gradients over the sample, and then forces move the edges to the top. So the most important properties which need to be known of the filament are the glass transition, the melting and the crystallization temperatures, the decomposition temperature, the expansion coefficient, and for the printed materials, it is good to know the thermal conductivity and a specific heat capacity. For these properties, we offer different measuring instruments. So the most important one are the DSC for the glass transition up to the decomposition temperature. The dilatometer can be used to measure the expansion coefficient, and for the thermal conductivity and specific heat capacity measurements, there are also several instruments and also the DSC. So the DSC is a differential scanning calorimeter, and it can measure the melting temperature, the melting energy, specific heat, glass transition, crystallization, thermostability, and also aging. And by that, one can specify then the filament a bit better, because it's very crucial to know these properties. The glass transition is of interest because here it gives information about a good temperature for the heated tray. So the temperature must be lower than the glass point so that the printing process is not disturbed. So by that, one knows how one needs to heat the build platform, and the melting temperature is of interest because the nozzle needs to heat up the material to higher temperatures than that, so that the polymer is really liquid, so that the printing process is can be really fluid and the material has a good property. So it is also crucial to know then the decomposition temperature. This can be also measured with a DSC depending on the polymer. So here one knows then the range from which temperature the material gets liquid and what is the maximum possible temperature which can be used for printing. So the Chip-DSCs are available in different configurations. So one is from room temperature to 450 centigrade Celsius. This is for the most applications good, but for example, if one wants to investigate then the printed material a bit further, or some polymers have also a really low glass point, so then some further configurations are possible. Here you see a picture of the DSC, and on the bottom you see this small sensor, which is put into the instrument, and in a very small crucible, one places then the material one needs to measure. There are also different heating rates possible. So the transition points are also depending on these heating parameters. So the faster the cooling, the properties can also change. So by that, one can really investigate the material in detail. Here are some examples for measurements performed by the calorimeter. So on the left, you see the glass point of ABS. So here a temperature-dependent measurement was performed from slightly above 40 centigrade Celsius to 200. And here you see clearly the glass point in the two curves, and you see that after or both samples here show a really similar glass point. So by that, you, for example, know that the heated tray should be lower than 106 or 105 centigrade Celsius to keep it slightly below the glass transition point. On the right, you see a summarized curve of PET. So here you see at around 80 centigrade Celsius the glass point, at 230 or 231 the melting starts. So you see here a rather broad melting peak, and you see also in this graph the crystallization. These informations are important for finding the optimum printing property settings. Here you can see a measurement of the glass point of PLA. And what is important here from these curves that the properties of the PLA change when during heating, so to say. So in the first run, the glass point is at roughly 60.5 centidegrees Celsius, and after the sample cooled down and was heated again, the glass point changes to around 67 centidegrees Celsius. So this glass point can shift to different directions, so to say, depending on the heating rate and also on the cooling rate. So this is also a crucial parameter because depending on the heating cycle and the cooling cycle, the mechanical properties of the then printed material can be influenced. And here you see a further example measured by the calorimeter. So here the melting of PP was investigated. PP has a glass transition at really low temperatures, so here only the melting was investigated. In the first run, one see a clear double peak. After the first heating, the peak changed, so it is only one. So this one here is smeared out, so to say, and after the third run, one can also see here the melting peak. So this onset point also changes slightly of the melting. And in the used materials, I mentioned those resins which need to be cured under UV light. And for the Chip-DSC, we also offer an add-on with which one can cure the material. So here you see in measurement, in this case, a mixture of resin was measured and it was placed in this Chip-DSC with this add-on, and by that it was irradiated with UV light pulses, and the measurement was repeated so many times until no change in the peak area was detected. So in the first peak, you see a clear difference to the last one, and here in the last peak, the area was the same as in the peaks before, so that the area reached a plateau, so that the material was cured completely. And this area under this peak here was used to calculate the heat of the reaction and the enthalpy for the curing. The next instrument which I want to shortly introduce is the dilatometer. The dilatometer can be used to measure the linear thermal expansion and the thermal coefficient, expansion coefficient. Sorry, there's a mistake in the presentation. So the CTE value. And it can also determine the glass transition. So in the curve, one typically can also see the glass transition. In general, the dilatometers can measure in a temperature range from -263 to 2800 centigrade Celsius. So there are several different setups which can cover different temperature ranges. For example, there's also one from room temperature to lower temperatures because a typical application of 3D printing is not up to 2800 centigrade Celsius. The instrument scheme is showed here. So for the horizontal setup, the sample is placed here and one has here a push rod which presses onto the sample with a predefined force, and one measures then the shift of the push rod during the measurement. Here you see an example of a dilatometer measurement. Here the linear thermal expansion of ABS and PC was measured. So you each see here a curve which shows the relative linear thermal expansion and the corrected one. The corrected one is just the relative one referred to the size of the sample at room temperature. So with the dilatometer, one can measure, as mentioned, the thermal expansion, and this can be used, for example, to also find out the right printing properties. For example, if the thermal expansion is really high, it can maybe lead to the material so that it stacks and too much material will come out of the nozzle. And the last group, which I want to present to you, are the thermal conductivity measurement instruments. For the polymeric part, the LFA, the THB, and the TIM tester are of interest. Each instrument measures in slightly different temperature ranges. So the LFA can be used for thermal diffusivity, specific heat capacity, and thermal conductivity measurements between general -125 to 2800 centigrade Celsius. And the LFA is the most universal tool since it can measure a broad thermal conductivity range as well. And one can measure several samples at the same time. The THB is a rather simple instrument, but it can also measure the thermal conductivity, thermal diffusivity, and the specific heat capacity. It is really easy and flexible to use because it's also really small. And it is a fully integrated setup. So there are also several furnaces and other accessories available so that measurements from -150 to 700 centigrade Celsius are possible, and it covers also a rather broad thermal conductivity range. And the TIM tester is also a thermal conductivity measurement instrument. It can also determine the thermal impedance of several materials. It can measure from -30 to 300 centigrade Celsius. The thermal conductivity range is a bit more limited, but here the advantage is that one can measure the thermal conductivity up to 8 megapascal, for example, so that one can realize maybe the application of the printed object. So in the next slides, I will shortly show you the working principle of the thermal conductivity measurements instrument. So in the laser flash measurement, one has a power source which shoots a short high energy pulse onto one side of the sample. Here the energy is then absorbed and a part of the energy is radiated onto the other surface of the sample, and this radiation is detected by an infrared detector so that one achieves a signal like that. And this signal is used then for the thermal diffusivity calculation, where also the thickness of the sample is of interest. With the THB, one has, as mentioned, a rather simple setup. So there are some foil sensors which need to be clamped in between two sample pieces. The sensor heats then the sample and measures at the same time the temperature increase of the sample. And from this information, one can then obtain the thermal conductivity. The LFA and the THB can be also used to determine the thermal conductivity of a polymer, for example, in a liquid state. The TIM tester works differently, so it's a steady state measurement method with two plates which heat up and cool the sample so that a stable temperature gradient over the sample is achieved. So one has a hot and a cold meter bar, and the specimen is clamped in between, like it is also shown here. And it is wait until the temperature distribution is stable. One measures here the thermal impedance of a material, and one measures 3 different thicknesses, so that one achieves a curve like that. And based on this information, one can then determine thermal conductivity range. But why is the thermal conductivity of interest? So thermal conductivity is more of interest for the printed material rather than the printing process, because the thermal conductivity of a printed material depends also on the printing direction and also on the layer thickness. Here you see an example of the thermal conductivity difference of printed PP and PP with CF10, and the printing was done under several orientations, which are shown here. And in this curve, you see that the thermal conductivity of the material is really influenced by the printing orientation. So by that, you can optimize your printing process in general to achieve, for example, the highest possible thermal conductivity of the material. Additionally, the layer thickness is also of interest. Here you see some cross-sectional scans of FDM printed structures with each a total thickness of 1.2 millimeter. The layer thickness ranges here from 0.1 to 0.3 millimeter. So you see here that really the layer thickness is of interest, since by that one can have more or less voids, so air in between the different layers, which can also influence strongly thermal conductivity. So here, a thermal conductivity measurement can also help to optimize the parameters. And on this slide, you can see some examples of polymer measurements done by the just mentioned instruments. So for example, here an epoxy was measured in dependence on temperature using the THB. Here you see an LFA measurement of PE, where one also measures up to the liquid or up to the liquid state. On the right, you see an plastic, which was measured by a TIM tester under several pressures, so 0.5 and 1 megapascal. And by that, one can, for example, investigate if the properties change under variable load. And here you see all of the results which were done for 3 different thicknesses of the material. Okay, so this was all from my side. I hope you now have a good overview of the printing processes and the used polymers, and which instruments from us with the thermal analysis can help to optimize the printing process. So thank you very much for your attention.